I'm Abhishek from the Google Open Source Security team, or GHOST in short. My talk today is about evolution of fuzzing in finding the unknowns. And today I will share this journey that spans more than a decade. From the lens of Google, we are collaborating with others in the community and driving some parts of this work directly. So first, a little bit about me. I've spent more than 12 years at Google, with the first 10 leading the vulnerability discovery and management in Chrome. I was the third person in the Chrome security team, and it was a real fun time finding bugs in browser back then. It was super simple to break things, as a lot of untrusted data was flowing in via these untrusted websites, and it was parsed without any validation. So hence, this was kind of a perfect ground for testing fuzzing capabilities. And now I'm leading the Google open source security engineering efforts as part of the GHOST team. And finding code vulnerabilities via fuzzing still continues to be an important aspect of it. We are also looking at several other areas. So for example, preventing supply chain attacks like SolarWinds code curve, where someone can actually just tamper the build artifacts in your CI/CD workflows and don't need to fight any code vulnerabilities and all. That's yet another interesting area of research. So how did it all begin? I can remember some of the early work to prototype fuzzing at scale in 2009 on Google Borg. For folks that don't know what Borg is, it's a cluster manager for all production workloads at Google. And Tavis Ormandy, a prominent security researcher, demonstrated a great prototype of fuzzing using more than 1,000 cores. And as far as I can remember, this was the early first example of corpus distillation, where you take gigabytes of data from the large Google search index and then really distill it to derive a small corpora of a few hundred files, but that hits the highest code coverage. The goal at that time was to find highly impactful bugs, and the best place to look at was just look at the recently exploited 0 days at that time. And Adobe Flash was a very widely exploited target at that time. In fact, some folks used to chuckle on a counter of days since Flash O-Day, and it would reset pretty frequently. So that's why Tavis took a crack at it. One of the important things to note here is super simple mutations like bit flipping went a long way towards finding a couple of hundred bugs. So very impactful. Now coming down to 2011, 2012, fuzzing was definitely showing its potential. But there was a lot of room for end-to-end automation. We had kind of a strong realization that fuzzing is a weapon of mass prevention, not destruction. But it needs to be hooked into the software development lifecycle, since the code was continuously changing. And it needs to be brought in the hands of the developers itself, not just the security researchers. So we worked out the early stages of this continuous fuzzing pipeline. And one of the early prerequisites that we realized was it has to be a very scalable process. We had a few dozen fuzzers at that time, but it was pretty clear that this system would have to scale to tens of thousands of first target, considering the fact that probably every developer at Google would be writing a few targets. So that was one of the requirements we had. Plus, automation was yet another key requirement. We cannot triage these hundreds of crashes manually, So we needed a pipeline to deduplicate them, and ideally in a fully automated way. So in those early days of bug finding was more around hooking into GDB, enabling some assertions, and hoping that the bug leads to a crash in this non-memory instrumented build. And contrary to what most security researchers think, finding the bug was one piece of the puzzle. An equally important piece was to assign it to the developer who introduced it, and also making sure that the developer fixes it right, because otherwise we would be ODing ourselves when the bug gets released. Now come down to 2012, 2013, comes the software sanitizers. They were very effective, just like the physical sanitizers we have been using in the last 2 years to keep ourselves safe. The reason for these was, as we were trickling down this bug stream, our developers gave us some pretty interesting feedback. Several of these bugs didn't reproduce. And that was the time we started collaborating with Kostia's team, which is the dynamic tools team at Google, who were thinking about efficient memory instrumentation. Some of the folks might realize, or probably already know, how crazy slow Valgrind is. Like, it would try to instrument each and every memory access and make your application 10 to 50x slower, maybe even more. And its startup penalty makes it completely unbearable for any practical fuzzing purposes. So fuzzing without any instrumentation was causing reliability issues. And we also missed several classes of bugs, for example, out-of-bounds reads. So that's where this was the period of the birth of these new sanitizer tools, which were addressing these different classes of bugs. For example, address sanitizer for common flaws like buffer overflows, use after freeze, memory sanitizer for uninitialized values, and so on. In addition to the sanitizers, another requirement that started coming up was the need for crash deduplication. Sanitizers in itself made the life slightly simpler because they would give a good crash type and had some reliable stack traces. But there were some more nuance of things that we had to figure out. Like, which parts of the stack are the most important? We would have the point of crash stack trace, we would have free stack for use after freeze, we would have the allocation stack. And when we analyzed those hundreds of bugs, it was quite evident that we probably only needed like the top 3 frames in the crash stack, pretty effective. And in allocation stack, we realized that it was not that useful. And the reason being, a large number of bugs usually impact a general class of objects. So to give you an example, in WebKit rendering engine, there was the DOM object node, and every second bug would actually kind of impact that one. So those were not really useful for deduplication, and we hence excluded those. Other things we were trying at that time was, when we got these bugs, we started analyzing them in the slow debug builds. And it became quite clear that some assertions, not all, like if you enable all the assertions in the build, you will get noisy crashes. But some of them actually pointed towards security implications. So we tagged these in a special way and enabled as part of the fuzzing instrumented builds. And this got a ton of badness as well. Now, coming down to late 2013 was this real revolution of fuzzing, when AFL, or American Fuzzy Lop, was made public by Michael Zielinski. This kind of took the security community by storm, as this was the very first application of usable coverage-guided fuzzing. And it especially worked very well on existing binary targets without modification. Its kind of effectiveness can be attributed to its innovation in several areas. For example, a novel program search space exploration using hit counts, several interesting mutators that worked on numeric values, byte blocks, and continuous corpus enhancements like trimming unneeded content, etc. This also actually inspired Costia's Dynamic Tools team to create their own version called LibFuzzer. But this was kind of targeted towards a different use case, towards making sure we fuzz particular API or endpoints. This was kind of novel in its own way, since it brought fuzzing closer to developers. They could write these simple fuzzers called fuzz targets, and that workflow was very similar to writing unit test. It also supported an in-process fuzzing mode called persistent mode, and this completely avoided the need of doing more forks, and hence provided increased performance. This feature was also added to AFL at a later time. So as you can see here, coverage-guided fuzzing was showing a tremendous investment on return. Usually, a fuzzer unit test would be less than 20 lines of code and would uncover several dozen bugs. As you can see here, this 5-line test uncovered all these memory corruption bugs in the popular XML parsing library libxml2. In the year 2014 and 2015, there were high-profile security incidents like Heartbleed, stage fright, and these were a big eye-opener for the industry on how ubiquitous open source software was and how it impacts critical infrastructure around the world. I'm kind of always fascinated by the effort that gets into finding these catchy names. It's kind of a pure innovation in itself. Like for folks that don't know about Heartbleed, it was a bug in the TLS implementation inside a heartbeat extension. And since it was leaking memory, that's where the code monicon named it Heartbleed. But jokes apart, this was a very unique opportunity we saw to help the community at scale by creating a free, easy-to-use service for open source developers called OSS Fuzz. Open source ecosystem thrives from the hard work of these volunteers in their free time. Security is usually the lowest on their priority list. So one of the key requirements for OSS Fuzz was making sure this integration with the OSS Fuzz service was less than 50 lines of code. And we wanted to make sure most of the workflow is fully automated. And thanks to fuzzing on tip of tree trunk or master branch, which is much closer to where developers are accustomed to committing and building, and OSS Fuzz ease of use, we had a huge uptick in new project integrations. Lots of new bug finds, but also lots of new bugs fixed. In fact, we had a 90% fix rate that was achieved in this kind of resource-constrained ecosystem. And you might not even hear these kind of numbers in regular enterprises. One of the other unexpected wins from this work was the community provided us a ton of interesting ideas on how we can simplify their lives, but in a way that helped to improve the underlying infrastructure as well. One of those examples was automated code coverage reports that they could leverage to improve their fuzzers. Another example was this concept of ideal integration, where we encouraged developers to put all of their fuzzing artifacts, not in the OSS first service, but actually upstream in the project repository and run them as part of the CI/CD system. What this helped was OSS first team would no longer need to track any maintenance on broken fuzzers as the code was continuously evolving. And this kind of led to the true scale of OSS fuzz adoption. We started with 15,000 cores, and now it spans a massive 100,000 core compute cluster, and it's running continuously on more than 500 critical open source projects and growing. Another important part of this journey was expanding relationships with both internal and external developer communities. We got many of the internal Google developers accustomed to writing these first targets via knowledge sharing workshops. And in a matter of months, we had several hundreds of first unit tests added across a variety of product areas. We would also gamify these with rewards like the swag you see on the left. And we would also highlight well-written and productive fuzzers in a leaderboard style setting. On the external side, we started the OSS Fuzz rewards program that would encourage these resource-constrained developers to integrate their projects with OSS Fuzz, but also encourage them towards writing high-quality, maintainable fuzz targets. Coming down to 2018 and 19, at this time, OSS Fuzz was providing great value to the community. But there was one use case that we still didn't solve. How can we make fuzzing simpler for enterprises that want to fuzz private code in a scalable way? There were many companies that reached out to us, for example, Salesforce, etc., and they wanted to collaborate and contribute to cluster fuzz code. So we decided that it is for the greater good that the backend infrastructure cluster fuzz should be open sourced. And this was a really interesting time because the fuzzing engines itself were not getting significantly improved. However, there was a ton of opportunity to improve existing thousands of fuzz targets. Developers were writing these fuzzers continuously, but several of them were not finding any bugs. And when we looked closer at many of those, there were kind of blunder but unintentional mistakes. As an example, first target would hit like a quick error condition and bail out, or it will be continuously leaking memory after every test iteration and ending early without building up enough state, or the corpus would just explode and the first target would be just stuck reading the corpus itself. We tried to capture all these metrics, surface them to the developer, and have a standardized way across all fuzzing engines on all platforms. And many of the things we actually tried to auto-fix where possible. Some of the other things we added was also automatic corpus cross-pollination, since we had thousands of these targets. And even though this was done in a more randomized fashion, it improved coverage in several first targets. So fuzzing was, at this time, fuzzing was widely recognized in the industry as one of the most productive bug-finding technique. Thousands of first targets written, thousands of security vulnerabilities found, but there was one problem, and actually a big one. There were a lot of research papers being written that made bold claims on their bug finding techniques against artificial benchmarks like lava, and it didn't replicate in the real world. There was development started on AFL++, a community developed version of AFL, but it was unclear how amazing it was and whether it was ready to replace the old AFL implementation. It was also unclear how AFL, fuzzer, and fuzz stacked against each other and why some of them were finding unique bugs on certain projects. We were looking at ways to answer this, but it was pretty clear there were three fundamental problems. The first one was there was no easy way to run these experiments. Each of these require at least 3,000 to 5,000 cores per experiment, and this was kind of hard to justify these kind of resources in an academic setting. The second problem was these experiments were not comprehensive and complete since they were run on a few artificial benchmarks on a small class of targets. Ideally, you would need a wide variety of targets, different formats, like let's say text-based formats, JSON, XML, versus image parser, binary formats, and so on. And the third problem, which was a big one, is all of this was a manual process. No one could guarantee that these fuzzing engines were configured right in their optimal setting before running these experiments. So to solve all these problems, several of us, like Jonathan, Laszlo, me, and others in the community got together and launched the fuzzer benchmarking platform called FuzzBench in the early 2020. As of today, more than 500 experiments have been conducted on the FuzzBench platform. This led to several improvements in the fuzzing engines like fuzzer and fuzz. For example, support was added for improved input scheduling, missing interceptors were added, etc. And note that these improvements automatically flow to tens of thousands of fuzz targets and led to finding of more bugs. We are also very happy to have supported the AFL++ team, like Mark, Andrea, Dominic, and others, with their FuzzBench experiment needs. They have conducted a significant portion of these experiments and really took AFL to the next level. I'm pretty sure you would have enjoyed Andrea's talk today on dissecting AFL. Also, FuzzBench is now cited in numerous research papers and quickly becoming a standard for fuzzer benchmarking. To give you an example, the entropic strategy from Dr. Marcel and team is now successfully integrated in fuzzer and helps to achieve the same coverage in just half the time for most targets. That's a pretty big win. We are also running private experiments to allow people to privately evaluate their research before publishing. So what's coming next? We had some thoughts on this front. The first thing is, let's create a more usable and impactful version of fuzzing coverage reports. Instead of throwing a lengthy multi-level coverage report over the wall to developers, we have started work on this project called Fuzz Introspector, which instead analyzes all the uncovered paths with the current corpus, backtraces them to common nodes, and then gives you a few prioritized functions that will cover most of the uncovered code if you add it as part of the first target. We will be testing this out with a few projects in OSS Fuzz soon, and need your feedback to really take it to the next level. I encourage you to chat with Navid, who is at the conference today, on this project. Another interesting project that is in the works is coverage-guided property-based testing. If you think about these things, they have been separate for a while. Like there have been property-based testing frameworks like Hypothesis in Python, where you can actually shape the inputs, define the mutators, but those were not coverage-guided. If you combine these two, you get the best of both worlds. So if you get a chance, I would definitely encourage talking to Laszlo, who's doing some very interesting work on this front. Another area that we should be exploring, and that was quite evident after Log4j incident, is we should be looking at non-memory corruption-related bugs that we can discover via fuzzing. There are applications of fuzzing beyond just crash bugs. If some of you remember the CryptoFuzz project in OSS Fuzz, that was a very interesting application of fuzzing to find correctness bugs in correctness bugs by comparing implementations of various crypto libraries. On a similar note, we could actually write sanitizers that can catch badness across privileged interfaces by adding those language level hooks. So things like hook into file reads, writes, network accesses, for example, in the case of JNDI lookups, etc. At this point, we have the capabilities to test new ideas, for example, with the FuzzBench benchmarking platform. We have the capabilities to run them at scale, for example, with the OSS Fuzz infrastructure. And we have the fuzzer pre-registration program in forums like today that encourage sound fuzzer evaluation. It's now up to you, the academic research community, on where you can take the fuzzing field from here. We welcome your ideas, and let us know where we can collaborate. This brings us to the end. Here are some ways to reach me and some of the fuzzing projects I mentioned, like OSS Fuzz, FuzzBench. I also highly recommend you to join the OpenSSF community meeting on fuzzing that happens monthly, and encourage you to brainstorm and collaborate on new fuzzing initiatives there. Thank you for listening. And with this, let's open the round to questions.
Thank you very much. Thank you very much for a very interesting talk, highlighting all these really valuable efforts from your team at Google. So we have time for questions. Matthias, okay, we can start.